The rest of the slides in this topic essentially are just practice problems. So I will work through these. If you want, pause the video so you can try yourself and think about them before I show you the solutions that I think are the best, or at least some different options on how you could approach this. So here we end up having a secondary amine. We end up having a few more qualifiers in here. We say that using only materials reagents containing 3 carbons or less. So especially this alkyl chain down here at the bottom, somewhere we're going to need to be breaking up into multiple pieces and bringing together. But let's first consider the disconnection possibilities for making the secondary amine directly. So the method we have that is probably going to be most effective will be reductive amination. Reductive amination involves retrosynthetically breaking either this bond or this bond and going back to the corresponding amine and the carbonyl compound. So this bond would probably be the best one to break because we could introduce this whole amine at once without necessarily synthesizing it independently because it has 3 carbons or less. So I will do this retrosynthetically. So going backwards, we would use the reagent combination of sodium cyanoborohydride. And we'd probably say catalytic amount of acetic acid. And that would lead us to a pentanone molecule, so a ketone with 5 carbons, plus our primary amine. Add my methyls on. Since this has 3 carbons or less, we are good to go here. We just need to finish the synthesis of this molecule. And there's a couple ways we could imagine breaking this up. Again, we're going to be looking for disconnections that largely break this bond. That'll get us back to a 3-carbon unit here and a 2-carbon unit here. We learned some new ways to make ketones in this section. One of them was addition of Grignard reagents into nitriles. So this would be using, say, this Grignard and acetonitrile. We'd be able to add these together, then with an aqueous workup would give this ketone. An alternative disconnection we learned in this semester or this topic that breaks the exact same bond is to use cuprates. So cuprates can also directly make ketones without the over-addition problem. In this case, we would just need to have the correct dipropyl long formal charge, lithium dipropyl cuprate, and acetyl chloride. Each of these would be able to give you that molecule to make the target as shown. There are some other combinations that you could also be using to synthesize this, but these are, I think, would be the most efficient ones that you have at your disposal. These next problems are actually quite similar to some of the ones we've seen before. This first example is pretty much directly out of both the notes and topic 2. So we know that we need to introduce a nitrogen group. It needs to be in the para position to methoxy. We know that methoxy groups are ortho-para directors. So we can just use nitration. We might get some of the orthoisomer as well, but we don't worry about that because we can't control it. And we can use pretty much any of our different types of reducing agents, tin chloride always being my preferred aryl nitro reducing agent of choice. This next problem is a little bit more involved, right? Because we end up having now to make a secondary amine. So secondary amines, we probably want to be thinking about reductive amination. And from reductive amination, we know that if we break this, we'd retrosynthetically go back to the corresponding ketone and methylamine. So this actually simplifies the problem quite a bit, right? Because now we know exactly how to bring in an acetyl group from topic 2. This would be a Friedel-Crafts acylation reaction with aluminum trichloride to go through the acylium intermediate. This gives us the ketone we need. And then it's just one more step to add in methylamine. We're going to add in our sodium cyanoborohydride and a catalytic amount of acetic acid. So again, something that looks to be quite a bit more complex and what may seem to involve quite a bit of few reactions is simplified quite a bit by recognizing that secondary amines are usually synthesized through reductive amination and getting back to that next ketone intermediate. Moving along, this next problem actually requires quite a few steps, so it looks like it's pretty straightforward. But somehow we're trying to turn a methyl group into a nitrogen. And so there aren't really many options here. We pretty much only have one way to install a nitrogen while also taking a carbon away, and that's the Curtius rearrangement. And that means that somehow we need to make this methyl group turn into an acid chloride. Acid chlorides come from carboxylic acids. So the first thing we want to do is actually fully oxidize this benzene ring, KMNO4, potassium permanganate, followed by acidic workup, will give us this carboxylic acid. To go to the acid chloride, we're going to use thionyl chloride. And this is all just to do different manipulations so that we can do the Curtius rearrangement. So the Curtius rearrangement is sodium azide and heat. This now gets us to the point where we have converted that carbon into a nitrogen. And then we can just add almost even water on workup would have worked probably for the case of the sodium azide. Isocyanates can hydrolyze pretty well. And these will go through a carbamic acid that decomposes and loses carbon dioxide to give the free amine. And now in this last problem, we need to simultaneously somehow make a primary amine and also introduce one carbon. So whenever we're looking to make primary amines and adding a single carbon unit, this will end up being a great job for using somehow a cyanide anion. So somehow we're going to be trying to attach a nitrile to this methyl group in order to reduce it and make it into a primary amine. So the first step is going to be converting this methyl into benzyl bromide. So we can do this bromination under radical bromination conditions. This can be bromine and light, or it'll abstract the weakest CH bond and recombine to make an alkyl bromide. Then we can add sodium cyanide. And we successfully introduce one more carbon into the molecule. And also the nitrogen we need. It's just in the wrong oxidation state. So we can use our lithium aluminum hydride reduction followed by water. Boom. Made a primary amine with one carbon added. So easy. This next problem was almost more of a sort of, fill in the reagent blank, follow the different reagents. And a lot of it has to do actually with just remembering some of the reactions from earlier in the semester. So the first is going to be electrophilic chlorination. Remember that we always need to add in iron trichloride as a Lewis acid along with chlorine gas to get this chlorination to take place. The chlorine will be a director for the nitration reaction, nitric acid and sulfuric acid, where the chloride deactivates the ring kinetically, but still will be an ortho-para director. Then we're probably going to have to heat this up with stronger chlorinating conditions. And we're going to get the second chlorine to go on now that it's further deactivated. Again, the most activating substituent ends up directing the group, so now this will go to the ortho position. Reducing a nitro to the aniline can be done with tin chloride. And the final step is simply making this amide bond. So we just need to go in with the appropriate acid chloride, add in a little bit of extra base, like triethylamine or pyridine, and now we have found a way to make the herbicide propanil from benzene in just 5 steps. So on the exam, you may need to use a little bit of the topic 2 chemistry. It probably would not be as exhaustive as this, but this is just to help bring back some of and refresh some of those reactions from earlier in the topic. All right, so now we have one last transformation here. And once again, we have a similar thing where we're trying to add on a single carbon and an NH2. So one potential way to do this is maybe we can be going through some sort of nitrile. So this is nitrile. So technically there are going to be a few different ways that you could approach this. I'll show you a way that we could go through and do this chemistry to install a nitrile directly. Something we learned from actually early on is that you can install a nitrile using Sandmeyer chemistry. So to do this, we can rely on the para-directing nature of the methoxy to first install a nitro group. This can be reduced with tin chloride, to the aniline, and then using sodium nitrite and HCl, followed by copper cyanide. Oops. I need to redirect this. We need one more step. Let me delete this. Move this over here. Will give us our nitrile. And the nitrile can be reduced with lithium aluminum hydride, followed by aqueous workup. There are some other answers that you could probably imagine that would potentially be maybe a little bit longer. You could be trying to go and turn this into a primary amide through perhaps making this Grignard followed by attack on CO2. That'd be more steps. But I think trying to keep in mind that whenever you need to add a single carbon and a nitrogen, trying to get to a nitrile is probably not a bad idea.